Hi, I'm Khiem, a business student at CMU. Our work is called WALT3D, generating realistic training data from time-lapse imagery for reconstructing dynamic objects under occlusion. I want to start by acknowledging that we have come a very long way in scene understanding, as you can see in recent years. But even with all this progress, occlusion is still a big challenge. In almost any urban traffic scene, you'll see all kinds of occlusions, whether it's between people or between people and vehicle. When we talk about occlusion, there's a concept called amodal scene understanding. Now, you might wonder, what does amodal mean? It is the ability to infer the whole shape of objects, even if part of them is invisible. For example, consider a scene with two cars, one in front, one behind. In this context, I want to make the contrast between modal versus amodal. First, let's look at modal predictions. For segmentation, only the visible part of the car behind is being detected. For key points, if you predict wrong key points for the occluded part and you fit a model to these key points, the 3D is incorrect. In contrast, amodal means identifying the entire car, including the hindered part. The same goes for key points. And with accurate amodal key points, you get accurate 3D predictions. In this work, we argue that one of the key challenges of amodal object reconstruction is the lack of data annotations. Why is getting amodal annotations difficult? Even for humans, annotating the occluded parts is not easy or accurate. For instance, in this image, if you ask 3 different annotators to annotate the car in the middle, you get slightly different answers, but they are relatively consistent because the car is fully visible. Now, for the slightly more occluded car behind, you start getting more variations because everyone has a different guess about the occluded parts. And finally, for the car out of your view, now the annotations are not consistent at all because a large part of the car is not visible in the image. And indeed, there's a very limited amount of annotations for amodal tasks, and this is just for 2D. 3D is even more limited. With better physics-based rendering tools, synthetic data is a promising direction. However, there's still a substantial domain gap, not to mention the huge modeling efforts to create a photorealistic dataset. To address this problem, many methods have tried to create occlusion by random copy-paste using COCO for 2D, or 3D you have Pascal 3D Plus datasets. And although this approach is very scalable, it often creates unrealistic image compositions. For concurrent works at CVPR'24, training data is also very important. For example, this work synthesized training data by automatically overlaying objects over natural images. Or in another work, these authors project the Matterport 3D object mesh onto the image to create the amodal mask. In our work, we introduce a novel method to synthesize realistic amodal supervision data from a different data source. Our goal is to create a dataset that satisfies these criteria. First, it must be scalable, no human in the loop. Second, it contains realistic occlusion configuration with both 2D and 3D supervision data. In this work, we are focused on vehicle and pedestrian because they are two of the most popular classes in the urban scenes. In our work, we leverage a very rich but underexplored source of data, time-lapse images. First of all, why time-lapse images? And the first reason is that there are many of them. With a simple YouTube search, we can access many publicly available video streams from all around the world. And secondly, these cameras record data over extended periods of time and they capture diverse occlusion scenarios typical of urban scenes. However, there's a problem. Although we have a very large amount of raw data, we face the same problem of no labels or annotations. What can we do? In our previous work called WALT, we can create a busy intersection with occlusion from raw time-lapse images. How did we do this? Let's look at this example. We first detect unoccluded objects in the scene, highlighted in yellow here. Although there's usually very few of them in an image, even if we are being very conservative, over long periods of time, you can collectively mine for even millions of them. Then, instead of random copy-paste, we simply place the objects back to the original locations, maintaining the correct scale and perspective. We also use off-the-shelf segmentation masks and pseudo-ground truths. Although this is better than random copy-paste, we are still relying on 2D information, and this sometimes results in unrealistic occlusion configuration. In this work, we propose a simple but effective extension of this framework to 3D. Given time-lapse images from a stationary camera, our goal is to automatically generate pseudo-ground truth data with a realistic occlusion configuration. Here, we show the composited RGB image accompanied by A-model key points, A-model segmentation, and 3D of humans and cars that come from off-the-shelf methods. First, we observe that off-the-shelf methods work well on unoccluded objects. Therefore, they can be used as pseudo-ground truth for supervision. Given a time-lapse video, we first identify unoccluded objects. Here, vehicle and human highlighted in yellow. Next, with the camera intrinsics and ground plane, we use off-the-shelf methods to get accurate 3D shape and pose of these unoccluded objects. In this case, the ground plane helps us determine the depth of the objects like humans accurately. We then copy-paste unoccluded objects back into the background image at their original location to preserve correct perspective from the farthest to the closest. As you can see here, each clip art image comes with a model segmentation mask, bounding box, key points, and 3D pose and shape. They are called pseudo-ground truths because they were predicted by off-the-shelf methods. This creates realistic and accurate occlusion configuration. Here, we show a full example of our 3D-based clip art data generation, where we composite multiple layers of occlusion of humans and vehicles. In this example, we have the clip art image and corresponding key points, segmentation, and 3D view. Let's step back and see the advantages of our 3D-based method. First, let's consider 2D-based method, where objects are cut and pasted at their original locations. If we look closer, we often see cars overlapping with each other and even pedestrians walking on top of cars. This does not happen with 3D-based compositing. Since we know the full 3D, we can composite a much more realistic occlusion configuration. Quantitatively, you can train faster with our data because our data is more realistic. Let's look at the plot. For every fraction of training data on the x-axis, we plot the mask accuracy on the y-axis. This plot shows that using our 3D compositing method has better training data efficiency, allowing us to scale to a larger number of scenes more efficiently. One crucial thing that we swept under the rug is how we obtain camera calibration and ground plane. For this, we use street view images to view the 3D scene and automatically localize the traffic camera with respect to the scene. Here, we show the traffic camera that we are interested in, and on the right, we show the localization of that camera within the intersection. Here, we show the point cloud, the ground plane, with the camera visualized in red. The render image from the point cloud also aligns very well with the actual image, showing the accuracy of our localization method. For more details, please refer to our paper. We want to emphasize that this approach is very scalable. We were able to localize more than 70 cameras across multiple continents, and this number will keep growing. With our method, you can turn any intersection into a crowded scene with full 2D 3D information that you can use as supervision data. Here, on top of the background image, we created the clip art image that comes with segmentation, key points, and also depth and normal that were rendered from the object shape and pose. This data can be used to fine-tune your favorite network for your specific task. Here we show another example of another scene. For proof of concept, we try to keep the architecture simple. We extend the masked RCNN base by adding a 3D vehicle prediction head for predicting the 6-dot pose and a 3D human prediction head based on XMR 2.0. This network is supervised by our pseudo-ground truth clip art data. Starting with a baseline model trained on standard datasets, we fine-tuned our WALT3D using 30,000 images from 6 cameras with about 3 million object instances. Next, we show some qualitative results. Back to the image in the first few slides, you can see that our model produced accurate reconstruction, especially of the occluded yellow car behind. Let's look at this image. If you look closely, it's a little hard to see, but there are 2 cars in the scene, with a car that is largely hidden behind. Our method is able to detect and produce accurate 2D and 3D reconstruction of people and all the vehicles in the scene. Here are some additional results from a video sequence. Notice the car at the edge of the image. Our method accurately predicts segmentation, key points, and 3D for all the cars in the scene. Note that these results are computed per image without any temporal information propagation. Similarly, pay attention to this car colored in red, which is heavily occluded. Check out the accurate reconstruction of this car even under severe occlusion. Similarly for people, our method is able to produce accurate 2D and 3D, especially when the person colored in blue is being occluded. Here, there is no trajectory smoothing and human is placed into a 3D view using the ground plane. Our method is also able to perform well in a crowded scene with accurate segmentation plus shape and pose reconstruction. Quantitatively, we want to look at robustness to occlusion percentage. In general, the more occlusion it is, the more our data helps. Let's look at 2 scenarios. First, we fine-tune and evaluate on the same camera. This gives us the best performance. So let's say if you have a few days of raw time-lapse images, you can achieve optimal results with this approach by training one model for every camera without any human labeling. And second, the improvement is smaller when we try to generalize to a new camera. However, remember that we only fine-tune on 6 cameras, and with more training cameras, we expect better generalization performance. On the MOT17 benchmark, using simple shot tracker, by fine-tuning the baseline person detector with our dataset, we see a significant improvement in tracking performance. Although tracking is not our main focus, we believe that tracking under occlusion remains an open research problem, and more progress can be made in this domain from both the detector and tracking perspective. In conclusion, we introduce a method that automatically generates supervision data from time-lapse images with realistic occlusion configuration. We show that using this data significantly improves training efficiency plus robustness to occlusion, leading to accurate object reconstruction on scenarios with high occlusion. In terms of weaknesses, our method still assumes a mean-shaped model for objects such as cars and humans. With recent advances in arbitrary object reconstruction, we hope to be able to relax this assumption. Second, although clip art cut and paste helps maintain the perspective, it's not perfect. With recent progress of the vision-based model, I think they can help tremendously to make it look more realistic. And finally, if you have time-lapse images from any stationary cameras and you want to improve your robustness to occlusion, please give our method a try. To end the presentation, I want to thank my collaborators, Dinesh, Robert, and Srinivasa, and thank you for your attention. Please visit our website for more information. Thank you.